Section 2.4, Understanding Amazon Aurora's Logging, Storage, Caching, and Indexing. In this video section, I'll help you understand Amazon Aurora's logging, storage, caching, and indexing, some of the most exciting innovations in Amazon Aurora's architecture. As corny as it might sound, I think of this section as Stairway to AWS RDS Heaven. You'll recall this image from video chapter 1.0 on Amazon Aurora's overview. I'm showing this image again because the backbone of the redesign of the relational database in a day where there's AWS is Amazon Aurora's service-oriented architecture applied to a database. This pivotal architectural change moved the logging and storage layer out of the database process and created a multi-tenant, scale-out, database-optimized storage service. The storage layer is now a service, similar to how Elastic Block Storage used by Amazon EC2 is a service. It lives outside the process and is a service-oriented architecture for accessing storage. The services in the control plane on the right side of this image are services that control the database itself, such as provisioning of the system, the metadata that has to be kept about the system, and some of the DNS features such as the endpoints when you launch an instance, and S3 for backup and durable storage. You've seen this image before too, when high availability was overviewed. This time, we're going to focus on the log structured storage section of the image, pointed to by the purple arrows. The log structured storage has many small segments, like you see represented in these small squares. However, they reside within the green rectangle nodes in the storage layer. Each one of these small segments has their own redo logs. Log structured storage isn't new. It's used in NoSQL products like Cassandra and HBase, where there's the concept of log structured merge trees, which is how those databases store their data. The Amazon Aurora team has done something similar, but with some unique characteristics. So what is log structured storage? When data is written to storage, it's appended to the end, just like a log file. You don't actually update anything. It doesn't bother to find the particular place on disk to find where the original value is, look it up, and write it back to that page. B-tree indexes hold pointers to the latest version of a record. What happens is when you write a new block or segment of storage, you're going to update the pointers in the index to point to the newest version of it. Remember from Amazon Aurora video chapter 1.0 when we discussed the update of parallel read-ahead? This is a feature that aims to improve the performance of B-tree scans, including range queries that don't fit in memory. It works by automatically detecting a page read pattern and prefetching pages into the buffer cache in advance of when they're needed. The existing InnoDB mechanism that prefetches pages by relying on a pattern that looks at similar physical page IDs doesn't work well in practice, as physical page IDs are not contiguous over time. So, in Aurora, they've implemented a logical read-ahead implementation based on the logical ordering of the pages. For example, based on the current relationship of the pages in the B tree. As soon as they see a logical pattern, they compute the logical successors of the current leaf page and trigger reads for those pages from Aurora storage. The system is capable of reading ahead pages of multiple tables at the same time within the same transaction. This means you're going to have stale data with nothing pointed at it. The Amazon Aurora team created a garbage collection process that periodically removes the old data. This image is a conceptual, not a logical, diagram of what log structured storage is, insofar as the indexes and the pointers are concerned. Looking on the top left, there's a B-tree index with primary keys in it. In a B tree, each segment points to another segment, which will eventually point to a leaf node. On the leaf node, you'll see Key 55 has a leaf node, value 1, whatever that may be, and Key 52 has a leaf node of value 1 or value 2, whatever that may be. Notice, there's a new value for Key 52. It just gets appended to the end of the block storage. Then you have to update the index. On the bottom image, you can see the new value is now referenced by the index node, and the old value is stale. It's no longer needed, so eventually a garbage collection process will come by and clean it up and reclaim that space. It's like compaction in Cassandra or HBase, where the files are flushed to disk, merged together into a smaller number of files, and what you end up with is updated records and a small number of files. There are some amazing benefits of log-structured storage. What log-based storage really means is that the database file itself is the write-ahead log. It is your replay log as you're writing out, appending these blocks to storage. That's basically what a write-ahead log does. This means your I/O is reduced because you don't have to do 2 writes now, which is write to the write-ahead log, then secondly, do what you said you were going to do in the write-ahead log, which is how databases work today. And also, you get almost instantaneous recovery from failures because the database file is the write-ahead file. So if the database fails, you just restart the database and start reading from where you left off. Update the pointers, and you're up by your replay logs as you're reading from the database. You can also cache the writes in memory, and when the buffer fills up, you flush it out asynchronously. When you cache the writes in memory, you end up with great consistent write performance because you're writing to memory and not to storage. This also means backups are continuous and incremental. Each new log segment is copied to the backup storage as it's completed. There's also what's referred to as multi-version concurrency control, which has to do with the fact that data is only appended, not updated. What that means is that when a client requests a read, the read is going to look up the bit of data via the pointers in the index. This means it's going to get the most current data at the time the read was requested. Someone could change the data while the client is reading it, but that's okay, because to that client, it got the most up-to-date version. If the client then wants to write a value back out, all you need to do is on the right, look to see if the pointer has changed from the value when it was read, and if the answer is yes, you have a concurrency problem. In Amazon Aurora, you can handle that optimistically as opposed to pessimistically, where you'd have to lock that data down during that transaction. Reads get a copy of the data in the exact state it existed when the transaction started with optimistic concurrency. This doesn't mean you're going to overwrite what someone else has written. It just means you can choose to do this, or you can choose to reread it and rewrite it. This solves a lot of scaling issues with relational databases' heavy use of locks, which can be burdensome. Quiz time for section 2.4, Understanding Amazon Aurora's Logging, Storage, Caching, and Indexing. Question: what is not true about Amazon Aurora's logging, storage, caching, and indexing? A. B trees don't have primary keys. They have corresponding leaves. B. It has a garbage collection mechanism. C. The database itself is its own write-ahead log. D. Caching is outside the database process and can survive a database restart. Answer: A. B trees don't have primary keys. They have corresponding leaves. Explanation: B trees do have primary keys. They point to other sections that eventually point to the leaf nodes. This concludes section 2.4, Understanding Amazon Aurora's Logging, Storage, Caching, and Indexing. Coming up next is section 2.5, Understanding Amazon Aurora's I/O.